This is joint work with my colleagues Ido Bentov, Pavel Hubacek, and Asaf Nadler. So let's start. I know you all know everything about Bitcoin. I'll go over this fast for, put us all on the same page. So for this talk, let's think of Bitcoin not as a cryptocurrency, but as a distributed consensus protocol. So how does it work? We have miners, and they compete to solve a puzzle, the proof of work. And now the first miner to solve the puzzle is elected leader, right? And the leader gets to decide what happened, the history of the last 10 minutes, and also gets a reward. So this is something very interesting and good. It's the first permissionless consensus protocol that actually works. Of course, there's some caveats. We need some assumptions. At least 2/3 of the hash power must be honest, and we have some assumptions on network latency and things like that. But it actually works. This is really nice. But it's not all good. So for example, one of the big problems with Bitcoin that lots of people are trying to solve with different protocols is limits on throughput. And these are due to network latency. Basically, you can show that if the latency is too large, compared to the throughput, then the malicious solvers get some head start, and then things go down. And there's also a very high variance and a long time to get a reward. And this is bad for Bitcoin also in terms of security, not just in terms of economics, because it really encourages centralization. So if you know that it's going to take you a year to get a reward, then you're much more likely to join a pool. And this is, in fact, what's happening with Bitcoin, right? Most of the hash power is concentrated in a very small number of pools. And finally, there are problems with the rationality of the protocol. What I mean by rationality, is it the rational thing to do to follow the honest protocol? And we know specifically for Bitcoin that it's not the rational thing to do. In fact, there are in certain situations cases where, for instance, it's better to withhold a block rather than to publish it. And this follows, at least in part, from this winner-takes-all type thing. Whoever publishes the block gets everything, and if you publish a block too late, you get nothing. So in this talk, I want to introduce Meshcash, which is a new framework for distributed consensus. By framework, I mean it's not a specific protocol. It's actually a family of protocols. It's a set of rules that lets you build protocols with nice properties. And some of our design goals are building a race-free consensus. What do I mean by race-free? So there's no leader election required. And it has very nice rationality properties. In particular, we built this protocol so it would be easy to prove that doing the right thing is the rational course. So in our previous talk, right, we saw that it's very hard to analyze these things, especially when you start adding rules and things get complicated. So we're sort of going from the other direction, saying if you build the protocol in such a way, sort of it's targeted toward making analysis easier, then maybe you can do things a little bit better. So what's the basic idea? We have what we call a tortoise protocol. Why? Because it's slow but sure. And it's going to guarantee consensus eventually. And it uses some ideas, so it's different from previous protocols because it uses ideas from these traditional or classical Byzantine agreement protocols that we've known for many, many years, but in a blockchain context. I see I'm using the old slides. Okay, and then we have a fast but unreliable Hare protocol, which guarantees, which doesn't guarantee consensus necessarily, but if it does work, then consensus is also very fast. And the second thing that we might think of this as an elephant and goldfish protocol, because the tortoise protocol, this long-term protocol, not only guarantees consensus, it also guarantees irreversibility, right? So that it's not enough for if we want to have a cryptocurrency, to say that we all agree on what happened. We need to make sure that things don't change. In the future, we still agree that what happened today happened today. So the Hare protocol, when you try to design it, it's much harder to design a protocol that has all of the properties. So now we're sort of splitting it up. We're saying you can design a protocol that just guarantees consensus on the recent time period, and the tortoise or the elephant protocol will guarantee that it's also going to be irreversible. Okay, so let's go into a bit of detail. First, we have underlying this protocol, like basically all cryptocurrency protocols that are currently in use, we have this gossip network. And we can use the same one that they use for Bitcoin or Ethereum or whichever one. The idea is you have a peer-to-peer network where every node passes gossip on to all its neighbors. And what we assume about this network is actually fairly weak. So we need it to be partially synchronous. And by that, we mean that there's some bound on the network delay, but not everybody gets messages in the same order or at the same time. And in particular, our protocol works under a very, very powerful malicious adversary that can control the network completely up to this bounded delay. So it can decide, it gets all the messages, and it can decide when it's going to deliver the messages to the node. So obviously it gets them first, and it can change the ordering. It can give different honest nodes messages in different orders. It can delay them up to the bound as much as it likes. Why do we do this? Why do we assume such a powerful adversary? In real life, probably nobody will be able to actually launch an attack this powerful. For the same reason that Silvio Micali in his talk yesterday said, in cryptography, we always like to assume the worst, so that if we don't know what's going on in real life, we can say that, as long as it's not this bad, we're still okay. Okay, so this is the gossip network in real life. Of course, in our protocol, we're actually using an abstraction of the gossip network where we abstract it as messages that are always broadcast. And when you want to broadcast a message, you just send it to the adversary, to the bad guy. This models this really, really powerful adversary. And the adversary chooses when to deliver it to every honest party. And there's this bound on how much it can deviate from one honest party to the other. Basically, what we're saying is that if one honest party receives a message M at time t, according to its own local clocks, we also don't assume that the local clocks are synchronized, then every honest party will get that message by time t plus delta, again, by their own local clock. So we're sort of bounding together the difference in the clocks and the difference in the message delivery. Okay, we also need a formal model to analyze this, to say what kind of guarantees do we get. And we're using a generalized blockchain model that was developed by Seeman and shelat. And here, as you'll see in a moment, our blockchain is not actually a chain, but you can still view it as a chain in this model, where the chain is this ordered list of messages. And in our case, we think of messages as blocks. And we have several security goals, and these are common, I think, to all cryptocurrency protocols. One is consistency or consensus, right? Everybody should agree on all but the last few messages in the chain. Why can't we agree on the last few messages? Because maybe we haven't all received the last few messages, so you can't expect us to agree on everything. We also need irreversibility. So at any 2 points in time, if we look at what I thought happened in history right now and what I will think happened in history 3 hours from now, then they should be the same, right? Blocks shouldn't be able to change. The order shouldn't be able to change over time. And we have some additional properties. We want this chain growth or liveness property, which means that if honest users want to add things to the chain, then they'll eventually be added to the chain. We don't want the adversary to be able to just block the chain completely and not let anything on. And we have something we call chain quality or fairness, and this has a big effect on the rationality analysis, which is that the fraction of blocks that are honestly generated, that are actually accepted to this chain, should be approximately equal to the fraction of blocks that are really generated by honest parties. Of course, that would be perfect chain quality. In some cases, we might get chain quality that's a little bit less. Okay, and finally, we have our basic tool, proofs of work. So we model them as this random oracle. I'm going to go over this very quickly because you all know it. And this protocol is based on proofs of work, but I think these ideas can also be used in other contexts, using something to replace proofs of work. Okay, so let's go over what Bitcoin does. So Bitcoin is a distributed ledger of transactions, and the transactions are partitioned into blocks. So each block has this list of transactions, and every miner tries to create the next block. How do they do it? They commit to the previous block and basically also to all the previous transactions. And then they run this lottery. This is what the proof of work looks like, basically. I'm running a lottery, and if I win, then I can broadcast my block. This is the successful block. So what are our consensus rules? Why am I going over Bitcoin, not one of the other things? Because Bitcoin is really, I think, the simplest one. So it's easiest to understand what's going on, and it will be easiest to compare to. So first, there's this chain rule, right? All blocks must have a valid proof of work. Otherwise, they're obviously wrong. But also, we have this additional rule. Only blocks on the longest chain are valid. So what do we mean by longest chain? If we have just one chain, then OK, all blocks are valid. Now we have a new block. We have basically two chains. This new block is not valid because it's not part of the longest chain. This one is part of the longest chain. 7 is not part of the longest chain. Now we have some arbitrary tie breaking. And if suddenly one chain becomes longer, then all the blocks on that chain suddenly become valid and the other ones become invalid. And we have some rules about transactions. So a transaction can only appear on a single block in a chain, and we should not have conflicting transactions in the same chain. So how do we order the transactions? We use the block ordering. So transactions in earlier blocks are earlier than transactions in later blocks. And inside a block, by the order they're listed inside the block. So one thing to notice is that it's actually enough to think about the consensus on the block order. Once we have a total ordering of blocks, we can always get the total ordering of transactions. So from now on, I'm going to ignore the ordering of transactions, just assume that I always take the order of blocks, and then inside each block, whichever order they appear in, and between blocks, if they're in an earlier block, then they appear earlier. If they're in a later block, they appear later. OK, why does Bitcoin work? It's because we're assuming there's an asymmetry in the hash power between the adversary and the honest party. So the adversary has a lower rate, a rate Q, say, where Q is something between 0 and 1. And the honest users generate blocks at a higher rate. So the honest blocks are generated at a rate 1 minus Q. And because Q is going to be less than half, then 1 minus Q is bigger than Q. So what does this mean? This means that the longest chain is always going to grow faster than shorter chains. Why? Because honest users always extend the longest chain. So the longest chain, because it grows faster, it's going to remain longer. And even if there are two chains that somehow had the same length to start with, and the honest users just flip coins to decide which to go with, at some point, with very high probability, one of those chains is going to get longer. And from then on, that chain will keep getting longer and longer, faster than the other chain. And the nice thing about this analysis, this is so original, I guess it's Nakamoto gave this the idea, but there's like a formal analysis that came later. The probability of ever catching up depends only on Q. So and how far ahead we are in terms of the chain. So this is why in Bitcoin, if we have, say, a 6-block advantage, and we assume Q is less than half, then we can bound what is the probability that blocks will ever be reversed. So it's a very nice property, and it makes this analysis, admittedly a slightly simplified analysis, but it makes it quite simple. OK, so that's what the consensus rules are. What about the incentives? So there are two types of rewards in Bitcoin. There are block rewards, which are given to the miner of every valid block. And they're the same for every block, ignoring the adjustments. And they don't depend at all on what is included in the block. So there's nothing, it doesn't matter what transactions are included in the block. And then there are transaction fees. So transaction fees are given to blocks depending on which transactions are included in the blocks. And this allows the users to pay for the miner's expenses. But right now, the transaction fees are basically negligible compared to the block rewards. So people, the economics of Bitcoin depend basically entirely on the block rewards and the speculation about how much more Bitcoin will rise. And I think basically all of the previous economic analysis of whether it's rational or not to follow Bitcoin's rules, they only looked at this setting where the block rewards dominate. Once block rewards stop dominating, things change completely in terms of the economic analysis, and things could really break down. It actually gets a lot harder to see what's going to happen. So that's one potential problem. There's also some more sort of hardcore problems. One is what we said, there's a limit on the block generation rate. So if delta was this bound on how long, what is the maximum time difference between what one honest party sees and another honest party sees, or think of it as the delay across the network, then we can't have the block generation rate be close to delta. Why? Because the adversary will always see the blocks first, the blocks they generated themselves, while honest parties start generating blocks basically that without seeing the previous blocks. So they're sort of splitting their hash power among many different blocks. And so security breaks down, and even before security breaks down, we have problems with fairness because the adversary always gets an advantage. And of course, because we have this limit on the block generation rate, it means we have to have a long wait time for rewards, because if we have many miners and a limit on how many rewards we get per time period, it means we have to wait a long time. And we also have limits on the size of the blocks, because if the block gets bigger, it actually takes it longer to travel along the network. It takes longer to transmit. So it means this delta grows. So if we want to have many transactions, right? If we want to have high throughput, we basically have two ways to do it. We can either make the blocks larger, but we can't because it will make the delay longer. Or we can make the block generation rate faster, but we can't because it'll kill our security and rationality properties. So these are pretty bad things. And this brings us to what's the motivation for Meshcash. So we want to have a protocol that has an unbounded block rate, regardless of the network delay. So we want to be able to have thousands or hundreds of thousands of transactions per second. And we want to make this protocol race-free. So we want to make the protocol have this really nice property that if you're an honest user, it doesn't matter what other users do, your reward is going to stay the same. And this is not the case, say, for Bitcoin, because if you try to mine a block and you publish the block, then now it matters whether somebody else published the block just before you or not. Right? So your reward could go from a high block reward to 0, depending on what somebody else managed to do. And why is this race-free property very nice? So think of a constant sum game, right, where the sum of the utilities is always constant. If I can't lose by doing the honest thing, it means that the adversary can't win by doing something bad, because the total the sum of the wins and losses is constant. So basically it means that if I can't gain by doing something bad, the rational thing to do is to just do the right thing. And this is in some sense not just slightly different heuristic, it's a qualitatively different type of permissionless consensus, because we're getting a consensus that does not use leader election at all. Okay, so now let's talk about how we actually do this. This is the sort of more technical part. So the first thing we do is we're going to extend this chain to what we call a mesh. A mesh is a layered DAG. And so think of, instead of having one block per time period, we have 100 blocks per time period, or in this picture, 3. Okay, why do we have to do that? Because a chain can't be race-free, right? There can only be one next block on the chain. And so if you want to have something that is not competitive in the sense that miners will always be guaranteed that their blocks get in, we can't have just one. So every layer is going to be mined concurrently. Different miners at slightly different times can generate their blocks. And what we get basically is that we can increase the throughput by just making the layer larger. So this is a parameter that we can tune. We can say what size layer we want. And the wider it is, the higher the throughput. So this idea of using a DAG is actually not new. It's been around for a long time. But the problem is that previous work that used DAGs always lacks something. So either they have no security proof, and why is this bad? Because in almost all cases where you have a complex system with no security proof, it's broken in some way. In fact, even if you do have a security proof, sometimes the proof is broken, but at least it reduces the likelihood of this happening a lot. Or they assumed that the adversary was rational. So they say, well, an adversary, it's not in his best interest to do something bad. But again, this is not always a good assumption in terms of protocols. Or they give up on getting full consensus. So I think the closest protocol to Meshcash is the Spectre protocol, which does something fairly similar. But they say, well, we don't guarantee a total ordering on blocks. We only guarantee that honest transactions will get in fast. OK, so how does the Meshcash mining algorithm works? The basic algorithm is pretty simple. What we do is we're going to point, every miner looks at all the blocks they see. Every block has this layer counter. So every block has a number that increases with the layer. Say I'm at layer 3. I look at all the blocks in layer 2, and I point to all of them, everyone I can see. And I also point to every block that has in degree 0. That's a block that nobody is pointing to. So if I see some straggling block somewhere that nobody has pointed to, even if it's not in a layer, in the previous layer, I also point to that, just so that I'll be able to show everyone, these are all the blocks that I see right now. And when do I go to the next layer? So remember, our clocks aren't synchronized. So we can't just say, after 10 minutes, go to the next layer, because maybe I think these 10 minutes have passed, but somebody else's clock is slightly different. So we don't use the time to go to the next layer. We count blocks in the previous layer. So if I see some parameter, this tmin is a parameter that we set for the protocol. So think of it as the layer width, more or less. So say if I see 100 blocks in the previous layer, then I increment my counter. Okay, and there's a caveat with this point to every block. I can't point to everything that claims to be a block. I have to check some correctness. So the correctness I check is what we call syntactic validity. So what is syntactic validity? It's something that can be determined by looking at the block itself and its successors in the graph. So what things can I determine? I can check the proof of work. It has to be valid. I can check the actual syntax, right? The format of the block looks right. And I recursively check that it's only pointing to syntactically valid blocks. So those are the syntactic validity rules. And finally, I can actually check that its layer counter is correct. Because, remember, blocks are only supposed to increment their layer counter if they've seen at least tmin blocks in the previous layer. So I can just check that it's pointing to tmin blocks in the previous layer. So that's syntactic validity. But that actually isn't sufficient to guarantee consistent ordering. Why? It's because honest messages receive the blocks in a different order. So even if I point to all the syntactically valid blocks, we might not agree about which order they're in. And we need a total ordering of the blocks. So what would happen if we just considered every syntactically valid block to be valid? Then there's one of two possibilities, right? Either we say the order is going to depend only on the structure of the graph, what it looks like, and not on the time at which I saw the blocks. So that's going to give us a consistent ordering, because all the blocks get the same content, so the order will be the same. But in this case, we can always somehow choose an ordering where the order is going to change over time. So I'm not going to prove this, but it's pretty easy to play around with this and see that this is true. And which means that if we did that, we'd violate irreversibility. We could always sort of add blocks later that would change the ordering for previous blocks. But if we didn't do that, so say the order doesn't depend only on the DAG structure, it also depends on the timing, now we don't have consensus anymore because the honest parties don't agree on the timing. Okay, so we also need some additional rules to decide on which blocks are valid, and we call those the contextual validity rules. Basically, anything that's not syntactic is contextual. So for Bitcoin, for example, this longest chain rule is a contextual validity rule, because you can't look at a block and say, is this in the longest chain? You need to know what other blocks are available. Okay, so what are the contextual validity rules for Meshcash? So this is where the tortoise and hare come in. So think of the timeline. We have on the left layer 1, and on the right, time goes to the right, and layer I is over there on the right. And now we have to decide on the validity of blocks. So if their blocks are far in the past, we're going to use the tortoise protocol to decide their validity. So the tortoise protocol has a set of rules that I'll show you in a moment that say what's valid and what's not. If the blocks are fairly recent, then we're going to use the Hare protocol. So the Hare protocol is not a specific protocol, it's just any protocol that we plug into this Hare slot. And we're going to use that one to determine validity. And if it's very, very recent, like this block has just been published, we might not know yet whether it's valid or not. We'll have to wait a bit. Okay, so what's the tortoise validity rule? This is for old blocks. We're going to vote on the validity. So to make this work, we're going to add this requirement that the block itself contains enough data to be able to reconstruct what the miner who generated this block would have voted had he voted at the moment of block generation. And that's going to be the block's vote. So in order to do this, we're going to modify the mining algorithm a bit. We said we're going to point only to blocks in the previous layer. We're going to add a new kind of edge, which we call voting edges. These voting edges are going to be edges to blocks in the recent layers that we are voting for. So why doesn't this just come out from the regular edges? Because maybe the Hare protocol tells us to vote for things depending on timing, depending on some data that I have that isn't part of the block. So I want to just record what the Hare protocol told me is valid and what isn't. So those are the voting edges. So I add these voting edges. And now I can completely reconstruct the vote. So what's the recursive voting rule? To give an example, we're going to see what, say, this top block that's in red thinks about the bottom block, 1. Okay, this is an example of how the voting rule works. So first of all, we're only going to use the blocks in the view. So anything that can't be reached via edges from that block, we're going to discard. Blocks that are very, very close, say in the same layer, that have basically no opinion about whether or not this one block was valid, vote 0. Blocks that are close, that are within the Hare protocol distance, are going to vote +1 or -1 depending on whether or not they have a voting edge to that block. And blocks that are further away, for instance, this top block, is going to just sum up all the blocks, all the plus and minus votes that it sees, and use that to decide. So if the sum is positive, then it'll vote +1. If it's negative, it'll vote -1. Okay, so why is this good? So first of all, it guarantees irreversibility. When does it guarantee irreversibility? If all the honest users agree on the validity of some old block with a large enough margin, so the difference between the plus and the minus is large enough, then every honestly generated block is going to vote +1. Because every honestly generated block is going to vote according to the miner's vote at the time it generated, and the margin is large enough that they're all going to agree. And now the adversarial blocks are going to be generated at a lower rate, just because this is our assumption. The adversary's hash power is lower than the honest party's hash power. And we get this same argument, just as we had for Bitcoin, that the longest chain goes faster. For basically exactly the same reason, the honest blocks will add to their vote faster than the adversary's blocks. So we'll always get the honest vote to be longer. Okay, so this is what happens if we all agree. But will we all agree, right? Will all honest blocks agree on the validity of the old blocks? So this depends on the Hare Consensus. So first notice that because we have this voting rule that depends only on the block itself, if two honest users see the exact same blocks, they'll vote the same way, at least on old blocks. But for recent blocks, we might not see the same blocks, because maybe I received a block and some other honest user, their block was delayed by the adversary. So here we use the Hare protocol. So if the Hare protocol lets us agree on all the blocks in the Hare interval, in all the recent blocks, so suppose we build somehow, again, this is a framework, so there are many different types of Hare protocols that give slightly different guarantees and have slightly different assumptions that we could use. But suppose this Hare protocol actually does guarantee that we agree on these recent blocks. Then the margin for the blocks is always going to be large because all the honest parties agree, and there are going to be more honest parties in each layer with very high probability than adversarial parties. And so we get consensus and irreversibility. So by choosing sort of a strong Hare protocol, we get immediately consensus and irreversibility, and it also starts almost from the next layer. So again, it depends on the Hare protocol, but it could start just at the very next layer. And unlike Bitcoin, where we have to wait for many blocks, here we're having, say, 100 blocks at once. So our margin is going to be large immediately for the first layer. Okay, so that's excellent. What about race-freeness? Why is this protocol race-free? Well, again, it depends on the Hare protocol, but if we choose the Hare protocol wisely, it'll guarantee that all honest blocks are considered valid by honest miners in the recent block list. But this means that these blocks will continue to be considered valid, so every honestly generated block is going to be considered valid. And this implies optimal chain quality. And because this is an easy property to analyze, we can also show that even in this transaction fee steady state, we get this race-freeness property. It's a little bit worse. We call it epsilon race-freeness, so you can lose a little bit. But it still gives you good guarantees about rationality. But okay, we said this Hare protocol might be unreliable. What happens if the Hare protocol fails? So this could be because you just chose a Hare protocol that's really unreliable, or because sometimes the assumptions are violated. Maybe the adversary launched a giant denial of service attack and caused the Hare protocol to fail. Then in this case, there's a problem because the adversary can keep honest users balanced between plus and minus for maliciously generated blocks. So I'm going to skip this because we don't have much time to show exactly how this happens. But this is the major problem, say, with Spectre. This is why they can't guarantee full consensus, because you can always sort of keep things balanced by adding plus, adding minus, and the honest users are always split, so they're never going to agree. You can keep the consensus from happening. So here we add an extra ingredient, which is a coin flip. So this is an idea from the traditional asynchronous Byzantine agreement protocols. We assume there's a coin that's broadcast at every layer start, and the miners add the coin value. So now the protocol for voting is going to change. Instead of having just either plus or minus, we have plus with a large margin, minus with a large margin, in which case we vote like before. Or we have somewhat, like we're not too far from zero in either direction, in which case we use the coin. So the idea here is that the honest parties can't be too far apart. So if all the honest parties are in the middle, between this plus minus theta, they're all going to vote according to the coin, then no matter what the coin says, they're all going to agree, because they all see the same coin. But if some honest user has, say, a definite positive plus because it has a large margin, because the honest users can't be far apart, then they're going to vote, some are going to vote plus and some are going to vote according to the coin, but they won't be split plus and minus. So with probability half, depending on the coin result, they're going to still get the correct result. And because this happens again and again, pretty soon they're all going to get voting in the same direction, and we can show that this guarantees consensus pretty fast. So to summarize, we have this new type of permissionless consensus protocol. It uses ideas from traditional asynchronous Byzantine agreement. It's secure against a very, very powerful adversary, allows a high block rate, and it has this really nice properties to analyze it in terms of game theory and rational consensus. And thank you.
Thank you, Tom. So we have time for one question. You're the closest.
Okay, really quick question. So maybe I missed this, but how is the double spend addressed in the layered approach, whereby I can spend the same pesos in my layer 2?
Yeah, okay, I didn't actually say that. So the point is, once you agree completely on the blocks and on the ordering of the transactions, if there's a double spend, it means there are two conflicting transactions, but you know their order. So you take the first one and the second one is invalid. Right? We don't care if the transaction is actually in the blockchain, we just know that it's invalid.
But which one is first if it's in the same layer?
If it's in the same layer, then you have a total ordering on the blocks in the layer, okay, say by block ID. So you can take it according to that.
Okay.
Thank you.